Problem number 3 is pretty straightforward, but I'm going to add a little twist. Now, they tell us that the sides of a square are increasing. So here's our square. And we know that it's going to bump out to a new square size like this, right? Whatever the length is here, they're saying it's increasing at a rate of 6 centimeters per second. So that would be a dl dt, because I used L for the length of the side of the square, is equal to 6. And they say at what rate is the area of the square increasing? So they're asking for the change in area and a change in time when the area of the square is 16 square centimeters. So they're also telling us area equals 16, which means, of course, that the length of a side would be 4. So we'll just put that in there. So here's the problem setup. Now, what do we know? Well, we know the area of a square. I hope you would know that. Is length times width, but because they're the same, we can say L squared. And they want dA dt. So let's take dA dt. The derivative of the area with respect to time is going to be 2L, but then chain rule dL dt. Because we're not doing it with respect to L. We're doing it with respect to time. Well, what do we know? We know the length is 4. And when they tell us dL dt is 6. So our answer is going to be 48 square centimeters per second. And that's the answer. So the trick here, which I did not do in the first couple related rates videos, was to say take dA dt is equal to dA dL, which would just be the 2L, times dL dt. Because if we do it right away this way, we can simply appreciate that that's what the chain rule is for. And it says the same thing, right? It says the same thing. We really did the same operation. So we'll move on to problem 4 and we'll apply it again.